All right, so in this lesson, we're going to continue chapter P, section 2. We're going to simplify some radicals. All right, now you guys have probably simplified radicals before, whether it was in geometry when you were doing right triangles or in algebra 1. All right, now typically you could use a factor tree. What I like to do instead is I like to extract perfect roots. I'll show you both in this example here. Now when the index is 2 and you want to maybe use a factor tree, we can say that 2 of the same factor appear once outside the radical. All right. Now, square root of 20, for example, you could maybe, and I know some people in class were able to recognize immediately that this is the same as the square root of 4 and the square root of 5. And the square root of 4 is a perfect square, and that's going to get you 2, so this is 2 square root of 5. Maybe if you didn't know how to do that, you could still use a factor tree, and maybe instead you used 2 and 10 and then did 2 and 5. You would still pick any matching pairs. So 2 is a matching pair, so that gets you 2. 5 is left over, so I get the square root of 5. All right, I know I wrote kind of small, but 2 shows up twice, 5 shows up once. All right, but no matter which way you do it, you should get the same answer. All right. Now with multiplying radicals, you can multiply 2 square roots underneath the same radical. So if I have square root of 2 and square root of 3, that's the same as the square root of 2 times 3, so the square root of 6. All right, now dividing is the exact same thing, right? Square root of 10 and square root of 5 is the same as square root of 10 divided by 5, right? So square root of 2. You can also go in the opposite direction for both multiplying and dividing. Let's say I gave you the square root of 6. That's the same as the square root of 2 times the square root of 3. Let's say I gave you the square root of 10 divided by 5. That's the same as the square root of 10 divided by the square root of 5. All right. Now, let's try some examples. All right. So, again, I would mostly try to find perfect roots. So something like the square root of 28, we can say that this is the square root of 4 and the square root of 7, right? It has a lot of factors, but 4 is the one that's a perfect square. I know that that's 2. Square root of 7, I can't simplify any further, so I leave it alone like this. Right? And we can do the same thing with 48. Right? So something like 48, a lot of people, when they pick perfect squares, maybe the most obvious perfect square is going to be 4. So maybe you do square root of 4 and the square root of 12. Right? And the square root of 4 is going to get you 2, so I get 2 square root of 12. But don't get tempted to stop here just because you picked one perfect square. You need to check whatever's left over to see if you can simplify that any further. And square root of 12, I actually can simplify that further. That's the square root of 4 and the square root of 3. And the square root of 4 is 2 again. So I have a 2 and another 2. Since these are both already outside the radical, I would multiply them together to get 4. And then square root of 3 is left over, so your answer is 4 square root of 3. If you picked a different perfect root, right, you want to keep in mind 48 is the same as 16 times 3. Now 16 is a bigger perfect square, and this actually gets us our answer right away. So doesn't matter how you do it, you should get the same answer, but some perfect roots are going to get you the answer quicker. All right, so just something to keep in mind when you're maybe under some time pressure, like on a test or a quiz. All right, now number 3, if I have a number in front, same exact idea, I would just multiply the whole number times the whole number. All right, so if I have the square root of 48, we just did that. I know that that's going to be 4 square root of 3. I have a 2 in front, so it's going to be 2 times 4 square root of 3. Again, I can do whole number times the whole number, and I get 8 square root of 3. All right, and nothing more we can do to that. All right, number 4, the exact same thing. This is the same as 6 square root of 9 square root of 5, right? 45 is the same as 9 times 5. And I picked 9 times 5 because 9 square root of 9 is 3. So I get 3 square root of 5, bring down the 6, and I can multiply whole number times the whole number. And so I get 18 square root of 5. All right? So just some more examples, same exact idea, 75, right? You want to think what perfect squares are a factor of 75. And it looks like it's 25 times 3. All right, and the square root of 25 is going to get you 5 square root of 3. I want to bring down that 14, so I get 14 times 5 square root of 3. And then 14 times 5, you can do it off to the side if you need to. You won't get a calculator, but this should get you 70 square root of 3. All right, if you look at number 6, actually, hang on, before I do that, number 5, someone said today in class that we can also make this the square root of 15 and the square root of 5. You can do that, right? In this case, you would just need to break it down as much as you can. So square root of 5, square root of 3, and square root of 5. Just break it down like a factor tree, actually. That's how I showed you guys before, so I'm going to do the factor tree. If you did 15 and 5, it would be 5, 15, and this would be 3 and 5, and you would still get the same answer because 5 is your pair, which we got here, and 3 was alone, which we got here. All right, and then you would still have to multiply by the 14 regardless. All right, so no matter which way you do it, you get the same answer. All right, and square root of 125 is the same as the square root of 25 and the square root of 5. All right, and I can bring that 10 down with it. Square root of 25 is the same as 5 square root of 5, and again, I can bring down that 10. I could do whole number times the whole number to get 50 square root of 5. All right. Now next one, 5 square root of 600. Think about what perfect squares are in 600, right? Our perfect square is going to be 100 times 6. All right, so I get 5 square root of 100 square root of 6, and square root of 100 is 10. So I get 5 times 10 square root of 6. Whole number times the whole number is going to be 50 square root of 6. And there's nothing more we can do to that, so we leave it alone. All right. Number 8, if I have more things being multiplied together, no big deal. I would still do whole number times the whole number, so 5 times the 2. And you can still do radical times the radical. So 3 times 3 is going to get you 9. But I know that the square root of 9 is 3. So I end up with 10 times 3, which is 30. All right. On that note, take a look at what happens here in number 9. Right? If I have the square root of 5 and the square root of 5, if I multiply those together, I get the square root of 25. And I could choose to multiply 9 with it and say that this is the square root of 25 times 9. So square root of 225, right? But that seems like a big number. This is a perfect square. It does get us a nice number, but maybe you wouldn't know that right off the bat, right? So what you can do instead is notice what happens. You can simplify square root of 25 and square root of 9 right away, and then see what happens when I get 5 times 3, right? That's much easier. That's going to get us 15. Now, the square root of 225 is indeed 15, so you will get the same answer, but notice that there's some things that you could do to make it a little bit easier. Just like with number 10, I definitely don't want to do 11 times 44 and try to find the square root of that big number. But what I can do instead is try to simplify the inside of these radicals a little bit more. So I get the square root of 11, and the square root of 44 is the same as the square root of 4 square root of 11. Square root of 4 is 2, and I have an 11 times 11, which is 121, but I know that the square root of 121 is 11. So I get 2 times 11, so 22. Right? And the pattern here, right, if you recall from class, it was around this time that I mentioned that a pattern happens, right? So if I have 2 of the same radical being multiplied, it just becomes that thing outside of that radical. So if I have the square root of 3 times the square root of 3, I could say that this is the square root of 9, which is 3, or I could just see that I have 2 of the same thing, so it's going to show up once outside the radical. Like 10 and 10, you could say that this is the square root of 100, or I can just notice that it's the same exact radical, so 10. And then I think at this point I had used a happy face as well. So a happy face times a happy face is just one single happy face outside the radical. Right, I could do a little heart as well. Square root of a heart is going to get us just a heart, right, outside the radical, as long as it shows up twice. Right, so it seems like a pretty basic fact that you guys might know, but it does make some problems a little bit easier. So you might notice 11 and 33 do not simplify, right? These stay exactly the same on their own. But there's something that we can do to make the problem a little bit easier. Even though we can't simplify the square root of 33, I can still split it up as the square root of 11 and the square root of 3. Because what happens here is I can do the square root of 11 and the square root of 11 to get 11. And then I still have the square root of 3 on its own, but this does simplify. Now notice that this is much easier than if I did 11 times 33 and gotten that big number and then tried to break it down that way, right? I don't want to do that. I want to opt for something a little bit easier. All right. Now, these next two examples involve dividing under the radical, right? So I had mentioned that with dividing under the radical, you're allowed to write it as that quotient under one single radical. So this is the same as 6 divided by 7 over, what am I saying? This is the same as 6 times the square root of 7 over 35. In class, I showed you guys something a little bit different, but seems like some people got it, but some people didn't. I think I had just divided the top and the bottom by 7, as long as they were both under the radical, right? But if they're both under the radical and they're being divided, you can just divide them, and this becomes 6 square root of 1 over 5. Now, just like with exponents, with radicals, you can split it up if it's 1 on top, 1 on the bottom, right? So I can do square root of 1 over square root of 5. And the square root of 1 is just 1, so I don't need to write it. We get 6 over the square root of 5, right? I know I did something different in class, so if this resonates more with you, what I'm about to do, then stick with it that way, right? So with 7 and 35, 7 I can take out a 7. 35 I can also take out a 7. And then I still get the same thing, right? I get 6 square root of 1 over square root of 5. And once again, square root of 1 is 1. So I still get 6 over the square root of 5, right? It doesn't matter how you do it, you get the same answer. Now, if you remember from geometry, you can't have a radical in the bottom. So what we do in this case is I have to multiply the top and the bottom by that radical that's in the bottom, right? Because use the fact that we established up here, right? 2 of the same radical gets you that number as a whole number, right? So that makes the bottom a rational number. So on the bottom, I'm going to have a 5, and on the top, I'm just going to have a 6 square root of 5. And then that is fully simplified. All right, I can do the exact same thing in number 13. 48 and 39, it looks like I can divide those two numbers by a common factor of 3. So if I divide 48 by 3, I get 16. If I divide 39 by 3, I get 13. So that means I get 5 square root of 16 over the square root of 13. Now, lucky for us, the square root of 16 simplifies. That's just 4. So then I get 5 times 4, which is 20, over the square root of 13. But then once again, I don't want a radical in the bottom. I'm going to multiply the top and the bottom by the square root of 13. All right, because 2 of the same factor shows up once outside the radical. And then on the top, I can't multiply a whole number in a radical, so I just leave them like this. All right, some more examples. All right, maybe a little bit more involved examples. Something like number 14. As long as I have a number out front of parentheses, the same rules of math apply. I can still choose to distribute that number to each term on the inside. Now the square root of 5 and the square root of 5, same thing twice, is just going to show up once outside the radical. And then minus 2 times the square root of 5, I can't do anything to that, so I leave it alone. And then this is your final answer. All right, some people aren't comfortable with that. Some people want to try to condense it into something smaller. You can't do it what I had told you guys in class, think of it like a variable. If I had 5 minus 2x, can't do anything to that, you just leave it alone. Same thing here. This 2 has a radical, but this 5 doesn't. All right, so I can't combine them. All right. Now something like 15, right? I have multiple radicals that I want to try to simplify. Like everything else that has a lot of steps, I'm going to do one step at a time, right? So I'm going to see maybe we can try to make this easier by simplifying everything in each parentheses. All right, so 3 square root of 2 looks like that's fully simplified. I don't need to do anything to that, so I'm going to have 3 square root of 2. Now, in negative 2 square root of 8, it looks like that's the same as the square root of 4 and the square root of 2. So that's going to get me a 2. So negative 2 times 2 is going to get me a negative 4 square root of 2. And it looks like this 3 square root of 27, that square root of 27, it looks like I can change that into 9 and 3. And this 9 is the same as 3. Or I'm sorry, the square root of 9 is the same as 3. So I can do 3 times 3 again, and that's going to get me 9 square root of 3. And then it looks like every single set of parentheses is simplified. So what I'm going to try to do now is do my whole number times my whole number times my whole number, or all my integers multiplied. I get 3 times negative 4, which is negative 12. And negative 12 times 9 is negative 108. All right? And then I can also do my radical times my radical times my radical. If I have radical 2 and radical 2, again, 2 of the same thing becomes that number outside the radical. So I'm just going to turn that into a whole number 2. So my only radical that's left is just 3. And then lastly, all I want to do is multiply this negative 108 times 2. You can do it off to the side if you need to. This is going to get you negative 216 square root of 3. All right, a little bit complicated of an example, right? Lots of steps to do. Show all of your work, right? Let's say I gave you something like this on a quiz. If I see that you're doing a lot of the work of simplifying the radical and maybe you mess up here, right? You'll get majority of the credit because you were able to simplify majority of it, but maybe you just made a silly mistake trying to simplify that or something like that, going from here to here. All right. So just something to keep in mind, show all your work when necessary. All right, let's continue. Something like 16, I have 15 square root of 6 divided by square root of 90. I can divide underneath the radicals. It looks like 6 and 15 share a common factor of 6. So I'm going to turn that 6 to a 1, this 90 to a 15, right? Divide the top and the bottom by 6, and then you get 1 and 15. And then so I get 15 square root of 1, but square root of 1 is just 1. And 15 times 1 is just 15. Over the square root of 15. Again, I can't have a radical on the bottom, so I'm going to multiply the top and the bottom by the square root of 15. Again, 2 of the same number is going to show up once outside the radical. And I can't combine a whole number with a radical, so I'm going to leave it like that. Now lastly, it looks like I have a whole number divided by a whole number, and that's just going to leave me with the radical 15. All right, keep in mind, I can't do let's say this 15 and this 15, because one's under a radical and one isn't. I can only cross out what are both exactly the same, right? Whole number 15 and whole number 15 are exactly the same, so you can cancel those out. All right. Now something like 17, I have 8 square root of 3 minus 6 square root of 3. These are like radicals, right? Just like how you combine like terms. If I had 8x minus 6x, those have the exact same variable, I can combine the coefficients, same exact here, right? 8 minus 6 is going to get me 2, and I keep the radical exactly the same. Let's say it was 8 square root of 2 minus 6 square root of 3. That would stay my answer. I can't do anything to that because they're not like radicals. Let's say it was 8 cube root of 3 minus 6 square root of 3. Even though underneath the radical is the same, this is a cube root, this is a square root, they need to be exactly the same, you would just leave it like that. So only when they match in every aspect can you combine the numbers in front. All right, let's apply that same logic here. Now, if it doesn't combine right away, you don't want to just say that it can't be simplified. What you want to try to do is simplify underneath the radical before you just give up, right? So notice that the square root of 24, you actually can rewrite that as the square root of 4 square root of 6. And then that's just going to become 2 square root of 6. All right? And then that negative 2 out front is just going to be negative 2 times 2 square root of 6 minus 3 square root of 6. And that becomes negative 4 square root of 6 minus 3 square root of 6. All right? And now those radicals do match. I can combine those. Negative 4 minus 3 is going to get me negative 7 square root of 6. All right? They're like radicals. You can combine them. All right, if you look at the next one, again, those radicals don't match. Let's try to simplify them. Square root of 45, we can do the square root of 9 and the square root of 5. That's going to be 3 square root of 5. All right, multiplying it with this 3 right here, 3 times 3 is going to get you 9 square root of 5. All right, and then 7 square root of 36, well, this, luckily for us, this is just a whole number. So 7 times 6 is just 42. All right, one's a radical and the other isn't. Can't do anything more to that. Just leave it like that. All right. Now, if you look at number 20, let's see if something similar happens here. All right, if I have the square root of 32, try to simplify it as much as you can. That's going to be 3 on the outside. Square root of 16 square root of 2. Minus 4 square root of 63, pick the perfect squares. It's going to be square root of 9 square root of 7. And so this is going to be a 4 right here. This is going to be a 3 right here. 3 times 4 is going to get you 12 square root of 2. Negative 4 times 3 is going to get me negative 12 square root of 7. All right, they are not like radicals, so I cannot combine them. I leave them alone like that. Maybe you see the 12s match and you're tempted to do something with those. You can't because these radicals are not the same. So you just leave it alone. All right. So now let's do some more multiplying. Here we have a binomial times a binomial. Now, in this case, in Algebra 1, you maybe remember that you can FOIL it. I could do first times the first, outer times the outer, inner times the inner, last times the last. So I could do 4 times 4, 16. 4 times negative square root of 11 is going to be minus 4 square root of 11. Square root of 11 times 4 is going to get me plus 4 square root of 11. And square root of 11 times negative square root of 11 is just negative 11. Shows up once outside the radical. All right, and look at what combines. I have a 6 minus 11, which is 5. Negative 4 plus 4 cancels out. They have the same radical, so you can combine them. You just get a whole number. Right? Now, in which case is it important for us to be able to turn a radical into a whole number? Right? If you remember, we did some examples where we wanted to rationalize a denominator and make it a whole number. Right? This might be useful to us later on, right? So just keep this fact in mind, that we multiplied 2 radicals and we got a whole number. All right? So 22, we can do something similar with multiplying and FOILing. What you don't want to do is you don't want to distribute that square to each of these terms, right? A lot of people are tempted to do that, right? You take a lot of mental shortcuts, right? You don't want to do it there. That will not work. So what you want to do instead, what does it mean to square something? Well, it just means to multiply it by itself twice. So I'm going to do 3 square root of 7 minus the square root of 3 times 3 square root of 7 minus the square root of 3. All right, and then you can FOIL it, right? First times the first. 3 times 3 is 9. Square root of 7 square root of 7 is just 7. All right, 3 square root of 7 times negative square root of 3 is going to be negative 3, and you can multiply underneath the radical. 7 times 3 is 21. Inner times the inner is going to be negative square root of 3 times 3 square root of 7. It's going to be the same exact thing, multiplying underneath the radical, and you can do negative square root of 3 and negative square root of 3. That's just positive 3. All right. Simplifying this more, 9 and 7 is going to get you 63. Negative square root of 3 and negative 3 and negative 3 are going to get you a negative 6. Square root of 21, we're allowed to do this because the radicals are the same. All right, and then plus 3. And then I can do 3 plus 63. So 66 minus 6 square root of 21. Nothing more we can do to that. The radical doesn't simplify more. Just leave it like that. All right, now with dividing radicals, I mentioned it in the previous slide, we want to never have a square root in the denominator. That's not considered simplified. So to simplify it, we do a process called rationalizing the denominator. All right. Typically, if it was just a number like this example right here, if it was just 5 square root of 2 or 5 over the square root of 2, you would just multiply the top and the bottom by the square root of 2. And so I get 5 square root of 2 over 2, right? Just by that radical. But if I have something like this example, if I try to do just the square root of 3 and I distribute it to each of those, it takes care of this radical. That becomes a 3. But then this one becomes 2 square root of 3. All right, so I still have a radical. So just doing this number is not enough. What you do is you multiply by the opposite expression. I also call this the conjugate. All right, the conjugate. So for example, here, the conjugate of 2 plus the square root of 3 is just going to be 2 minus the square root of 3. All right, and then I'm going to do the same thing to the top. All right, whatever you do to the bottom, you do to the top. All right, on the top, you would simply just distribute. You would get 4 minus 2 square root of 3. And on the bottom, you can choose to FOIL it, and I'll show you what happens when you do. If I do 2 plus the square root of 3 times 2 minus the square root of 3, first times the first, I get 4. Outer times the outer, I get minus 2 square root of 3. Inner times the inner, I get 2 plus the square root of 3. And last times the last, I get minus 3. All right, but notice the middle two terms cancel, and you end up with 4 minus 3, which is 1. So on the bottom, I'm going to get 1. And then this is just going to become 4 minus 2 square root of 3, right? Anything times over 1 is itself. All right, the shortcut here is you can square the first and square the second. All right, so I'm going to use a different color. So this is the same as 2 squared minus the square root of 3 squared, which is still going to get you 4 minus 3, so 1. All right, just a shortcut if you want to save a little bit of time. If you think you're going to mess that up, just write it twice and FOIL it. All right, so something like these examples here, if I have 7 square root of 2 over square root of 3, right, this is a case where I very simply just have to multiply the top and the bottom by the square root of 3. On the bottom, you get whole number 3, and on the top, 2 times 3 is 6. They're both underneath the radical, and I can leave the 7 alone out front. All right. Now, with 24, I can multiply the top and the bottom by the square root of 3 to get rid of that radical on the bottom. That's just going to become whole number 3. And then I can distribute that square root of 3 to everything. I get 4 square root of 3 plus the square root of 6. Nothing more you can do to that, so I leave it alone. All right. Now, this is a little bit of a new one, right, where you would need to use the conjugate, right? So if I have 1 over 3 plus the square root of 2, what I'm going to do is I'm going to multiply the top and the bottom by the opposite expression, so 3 minus the square root of 2. All right, now 1 I can distribute to everything, and that's just going to get me the same thing, right? So 3 minus the square root of 2. And on the bottom, you could FOIL it, but let's see what happens when you use the shortcut. I get 3 squared minus the square root of 2 squared. That's going to get me 9 minus 2, so 7, right? Gets you the exact same answer, just a little bit shorter. All right, and you can do the same thing with 26. All right, so 1 plus square root of 2 on the bottom, I'm going to multiply with the conjugate 1 plus square root of 2. All right, now on the top, you would have to FOIL. So I get 3 plus 3 square root of 2 plus 1 square root of 2 plus 2. And on the bottom, you can do the shortcut. Right, 1 squared minus the square root of 2 squared. You can FOIL it if you think you're going to mess it up, but this is just a shortcut. All right, so then 3 plus 2, I can combine everything on the top, is going to be 5. 3 plus 1 is going to get me 4 with that square root of 2. And on the bottom, I get 1 minus 2, so negative 1. And you can leave it like this. This is perfectly fine. Or you can split up that fraction. So 5 over negative 1 plus 4 square root of 2 over negative 1. But if you do it, some people are tempted to just do one of these. Like maybe you're just going to do that and you're going to leave this positive, right? That is not the case. You need to actually do it to both of your terms on top. So if you have a denominator, that has to be under both terms. So then you get negative 5 minus 4 square root of 2. So that's also equally correct. All right, so this, oh, whoa, let me rewrite that. So this is fine, or this is fine, either way. All right, if it's something like let's say, for example, this is a 5, so you get a negative 5. You can choose to do the same thing, right? Maybe you want to do 5 over negative 5, but then you would have to do the same thing to that 4. You would have to be 4 square root of 2 over negative 5. And then that becomes a negative 1. That stays the same, right? If it was something like 6 plus 4 square root of 2 over 2, let's just say, I'm making stuff up now. 6 and 4 can be divided by 2, so you should simplify this fully. 6 over 2 plus 4 square root of 2 over 2. And then this is going to become 3 plus 2 square root of 2, right? All this is just extra stuff. So if you understood it from here, then by all means you can continue. But just some extra stuff for you guys to consider. All right, let me just get rid of that just so that you can see the final product. All right, and that wraps up this lesson.